All right, the shape is the distribution of data. The shape of the data, the shape of the graph, is how the data is distributed. It's how it looks. And there are typically three things that we talk about. If I was going to talk about the shape of a graph, of this representation, I would first maybe look to say, is it symmetrical? If something is symmetrical, how could you describe that? Like, what does a symmetrical graph look like? Carly?
It's equal on both sides.
Yeah, it's equal on both sides. Elementary school, you learned this idea of symmetrical, like you put paint on one side of the paper, folded it in half, peeled it open, and it's this, right?
Wow.
Symmetrical. This is also called a bell-shaped curve. In the world of science, in the world of statistical analysis, a bell-shaped curve means that it's perfectly symmetrical. It starts out low, it slowly rises, it comes to the top, and it slowly goes down. It makes a hill. It's a bell-shaped curve. We could also talk maybe about the number of peaks. Maybe it's not symmetrical. Maybe there are two peaks. Maybe your data goes up, 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 then down, then goes back up. Maybe there are two, what would those two highest points of your graph be called? Two, not maximums. Modes. Maybe there are multiple modes. Or maybe there's a gap in the data. Like maybe you've got all of this data down here, then a gap, and then a whole bunch of data up top. Maybe there's a gap in your data, so there's a peak. We also talk about this idea of skew. So there is left skew. And if you think about a number line, on the left side of the number line, it's also called a negative skew. Or a right skew, meaning it's positive. So we talk about, is it symmetrical? How does it look, right? Is it beautiful? If it's not symmetrical, then we look to see, are there like multiple peaks? Is there a gap in the data? Do you have two modes? Maybe you have three modes. Or we look at the skewness of it. So if I'm looking at this histogram right here, if I look and it goes up and there's a little dip right there, so you could talk about how there's a little dip right there, but there's even more evidence of one of these three elements, and it's right here. My data is pulled to the right. Do you agree with that?
Yes.
And here's how I have to think about it. This is not a right skew. This is called a left skew, or it's skewed left. And here's how I think about it. This data got skewed on the left.
What does that mean?
Screwed.
The left side of this data, it's skewed.
Why did they have to do that? So it's like,
Why couldn't they just center it? That's when gas prices were
So what this means is that the median, which is the actual middle of this data, it's all the way over here, right, is greater than the mean. The actual middle of this graph is greater than the mean. What about this data? What can you tell me about this guy? Okay, it's a right skew. The right side of this graph got skewed.
Whoa. The mean is greater than the median.
Guys, where he gets a question mark on
Oh.
So that means the mean is greater.
That's when gas prices went back down. I don't think that ever
That's the
happened.
feeling you call
It
me.
went from like 356 to like.
We've also got these two extra little dots, which we'll talk about in a second.
Look, guys, look. If you connect it with the line, you can make it a curve.
What about this data? There are two peaks. So that means that it's bimodal. All right, we've got two peaks, which is bimodal. So we talk about the shape of the graph, but we don't just talk about it in generalities. We need to use these mathematical explanations or descriptions. We need to talk about, is it symmetrical? We need to talk about the number of peaks. What does it mean if there are multiple peaks? You don't just say there are two peaks. What does that mean? It means that there's a gap in the data, or it means there are multiple modes. We talk about the skewness, meaning that if it's left skew, that means most of the data is in the upper part of our data values. We do have some really low pieces of data comparatively, so that's making our data skewed on the left because the lower frequencies are not as often as the upper frequencies. Then we talk about outliers, and outliers are data values that are greatly different. But there's a problem with that definition. Because when I say data values that are greatly different, that could mean something to me, and it could mean something else to you. For example, I think just with this general description, there are two possible outliers. Can you pick out one of them and defend it? What would be a possible outlier in this data set? What do you think, Luis?
The 4.
The 4. Why do you think 4 could be a possible outlier?
Even number.
It's the only even number. I mean, I think that's a valid argument for this definition. You can say 4 is an outlier because every other value is an odd number. Not divisible by 2. This number is divisible by 2, so it would not be part of that data set. Zachary, what other number?
15, because it is a great inner number, and it's pretty far away from all the other values, which are relatively close to each other.
Okay, so we're talking like from 3 to 4, you go up 1, 4 to 5, you go up 1, 5 to 7, you go up 2, 2 to 7 to 9, you go up 2, and then we've got a jump of 6. We could also say 15 is a 2-digit number, where the rest of them are single-digit numbers, right? But I don't know if these are truly mathematical descriptors, right? So we have a formula we use, and the formula is as follows. The IQR, which stands for interquartile range, times 1.5, which is 150%, plus or minus the quartile. So we do 1.5 times the interquartile range, and we get an answer. Let's pretend that answer is 2. Then I add that number to the upper quartile and get an answer. And I subtract that number from the lower quartile. So I find my interquartile range. I multiply it by 1.5%. I add that value to my upper quartile, and I subtract that value from my lower quartile. This is the range that tells me what can be considered an outlier. So let's practice. The inner quartile range of this data set, well, that's the maximum, minimum, maximum, minimum, maximum, minimum. What's my median? 6. Then I'm going to find my lower quartile, which is 4, and my upper quartile, which is 9. Are we good on this? So my inner quartile range is 9 minus 4, which is 5. My inner quartile range is 5. Because I took my upper quartile minus my lower quartile and got my inner quartile range. And then now I take 5 times 1.5, and I get 7.5. 1.5 times the inner quartile range. I take this value and I'm going to add it to my upper quartile. 9 plus 7.5 is 16.5. And I subtract it from my lower quartile. 4 minus 7.5 is negative 3.5. If your data value that you think is an outlier falls outside of this range, it is, yes, an outlier. Is 15 outside of this new range? No. So technically, mathematically speaking, there is no outlier.
Except for 3. 3.
No, because it's negative 3.5, right? If this 15 was 20, it would be considered an outlier. But it is 15, not an outlier.
16.51 will be an outlier.
Put this to the side. Center. There are 2 centers that we talk about. There is the middle of the physical graph. Like if I folded it in half, that's the physical middle. It's the center. There's also the mathematical middle, which is called the median. So if I'm looking at this first histogram, the physical middle is right there. Where do you think the mathematical middle is? Right there. These middles match up. Because it's what kind of shape?
It's a
It's a bell-shaped curve. It's symmetrical. The middle, or the median, is in the middle. It's beautiful, right? It's a perfect graph.
Stop bragging, this is
I'm just saying, you have to get nerdy with this stuff and appreciate it.
Technically nothing.
Here's this. If I folded it in half, here's the physical middle. So if I was talking about the center, I could talk about the skewness of this graph, right? What side is skewed?
right.
This is a right skew, a positive skew. I could maybe talk about the gap. I could see, is this technically an outlier? I don't know because I don't have my correct data, right? I don't have my actual data to figure it out. So I could talk about the possibility. I could talk about the gap. Can you talk about the center of this graph? The mathematical and the physical center?
Yeah.
The median is where?
Like,
Median's on the left.
The median
towards the left.
is to the left of center. Meaning my data is clustered towards the bottom, towards the lower end. So I can talk about the physical center and the mathematical center. And then we go on to spread. And spread is the amount of variability. Some of us struggled with that term when we did our task cards. If something has a large variability, it means the data is
Large.
spread out, right? It's a large data value with a low minimum and a high maximum. If your variability is small, it's more compact. Your data is not very spread out. The spread of the data. The most common is range. We talk about the range of the data a lot. If you forgot maximum minus minimum. Sometimes we talk about the inner quartile range. Still a range, which is the upper quartile minus the lower quartile. And here's an example of like why I would talk about the inner quartile range. If I had a box plot that looked like this, I would not talk about the maximum minus the minimum. I would talk about the upper quartile minus the lower quartile. Because remember, in a box plot, this is 25%. And this is 25%. So half of the data is really spread out. The middle half of the data is really spread out. So I would talk about the inner quartile range here. I could also talk about the mean absolute deviation. And remember, you can find the mean absolute deviation compared to any type of value. You could compare it to the mean, you could compare it to the median, you could compare it to the mode. It just depends on how you want to do that. But the closer it is to 0, the less variability, right? If your mean absolute deviation is 3, and then another set of data has a mean absolute deviation of 17, that means that group of 17, that 17 mad, is really spread out. That one with the 3 is pretty clustered. These are called clusters. If I was going to make a dot plot that represented the average overall age of people who are physically inside the building of Hawker Grove, would there be a cluster?
Yeah.
Yeah, there'd be a cluster of 12, 13, 14, 15-year-olds. Would there be another cluster?
Yeah.
Maybe.
There'd be a cluster of 20s, 30s, and 40s, 50s, right? But there'd be clusters.
Teachers.
Oh.
And if you're talking about a histogram, the spread can be affected by bin width changes.
Oh yeah. I wasn't that.
If you have a bin width and your range of your bin width is 5, and all of a sudden you change your bin width range to 15, your data is going to be less spread out. It's going to be more compact. If I was looking at this box plot. Use the electric one. If I was going to use spread to talk about this, if I was going to talk about the spread of this, how could you talk about the spread of this data? What could you say about this data? Is there a cluster? Where? This is quadrant 1, right? Or part 1, quartile 1. Quartile 2 and quartile 3. Right? And then we have quartile 4 over here. I could say that most of my data is clustered where?
No, to the left.
To the left.
To the left.
75% of the data is below, let's go, 26, 27, 28.
I'd say 27.
I say.
27.
Yeah.
75% because each quartile is 25%, right?
Yes.
So there is a cluster. If I was talking about the spread of this data, I would say that most of the data is below 25%. I could also say that the top 25% of the data between 27 and about 60, I could say that that data is pretty consistently spread out. Because if that data up there was like 27, 27, 30, 30, 30, 30, 60, that 60 could technically have a possibility of becoming an outlier. So since it's not an outlier, I would guess that the data is probably fairly evenly distributed between these two values.
Another half hour of math left.